In this video, I'd like to talk about limiting reactant stoichiometry calculations as described in Chapter 9.3 of your textbook. We learned earlier in the unit that all stoichiometry problems begin with a balanced chemical equation. For example, 2A plus B forms 3C. We learned that this means that for every 2 moles of reactant A, we need 2 moles of reactant B to completely use it up, and we expect to get 3 moles of product C. Here are the types of problems we saw. For a given mass of A, what mass of B do we need to completely use it up? And what mass of C do we expect will be formed? Or, for a desired mass of product C, what masses of reactants A and B do we need? Well, let's consider the first question. For a given mass of A, what mass of B do we need? Well, we're starting with the mass of reactant A, and we know we can't do anything with the mass of A until we convert it into moles of A by dividing by the molar mass. The second step of any stoichiometry problem is converting from moles of one component to moles of another component by multiplying by the mole ratio. And then in the final step, we convert from moles of B needed to mass of B needed by multiplying by the molar mass of B. These types of stoichiometry problems are sometimes called ideal stoichiometry problems because we have ideal number of moles and masses. Everything gets used up and nothing is left over. But what if that's not the case? Let's begin with a culinary example because food is one of my favorite topics. One of my favorite things to make is multi-grain pancakes using the pancake mix from Trader Joe's. And here is the recipe on the back of the box. For every 2 eggs and 2 tablespoons of oil and 1 cup of milk, I need 2 cups of mix, and I will get out 14 pancakes. I've done this many, many times, so I know these to be correct. Did it ever occur to you that a balanced chemical equation with coefficients telling you how many moles of each reactant you need and how many moles of product you get is just like a recipe that tells you the relative amounts of ingredients you need and how much yummy food you're going to get? Well, they're exactly the same thing. So here's an example of a calculation you might do in your kitchen. If I have 3 eggs and I want to use them all up, how much milk do I need? Well, begin by writing down what you're given. 3 eggs over 1 if you want. And then to figure out how much milk I need, I go to the recipe and I write down an ingredient ratio. 1 cup of milk is needed for every 3 eggs, or 1.5 cups of milk. I tell you, if you have ever scaled up a recipe, you have done a stoichiometry calculation. Now, if I have 3 eggs, how many pancakes can I make? Again, start by writing down what you're given, 3 eggs, and I'll multiply by another ingredient ratio that tells me I will get 14 pancakes for every 3 eggs, or 21 pancakes. Now, here's where it gets a bit more complicated. Suppose I have 4 eggs and 6 cups of mix, and I want to get as many pancakes as I possibly can. Well, if I go back up and look at the ingredient list, I will see that I need 2 cups of mix for every 2 eggs. If I have 6 cups of mix but only 4 eggs, I can see that eggs are the limiting ingredient. They will get used up first, and they will determine how many pancakes I can get. If I calculated how many pancakes I could get starting with 6 cups of pancake mix, I would get the wrong result because I clearly don't have enough eggs for that much mix. So I will start with the limiting ingredient, 4 eggs, and multiply that by 14 pancakes for every 2 eggs to give me 28 pancakes. which is a lot of pancakes, but they freeze well, trust me. But then that asks the question, how much mix will be left over? Well, what determines how much mix will be left over is how much I started with, namely 6 cups, and how much gets used up. What controls how much mix gets used up? Well, of course, the limiting ingredient, which is eggs. So to calculate the amount of mix that's left over, I will start with the amount that I am given, and I'll subtract the amount that's used up, which is dependent upon the limiting ingredient, 4 eggs multiplied by 2 cups of mix for every 2 eggs, or 2 cups of pancake mix left over. If this makes sense to you, you understand limiting reactant stoichiometry. So now, let's apply this to a chemical reaction. Aluminum reacts with fluorine. What's that blank space for? Well, of course, for writing and balancing a chemical equation. I expect you to know at this point that aluminum is a monatomic solid, fluorine is a diatomic gas, and to predict the formula of the product formed between this metal and the nonmetal, we need to write the symbols of the ions formed. Aluminum forms a cation with a 3+ charge, fluorine forms an anion with a simple negative charge, so the formula will be AlF3. I also expect you to know that pure ionic compounds are solids. To balance this, we need a 2 before the aluminum fluoride, a 3 before the fluorine, and a 2 before the aluminum. So, just as was the case with my pancake problem, I'm going to begin with specified quantities of both reactants. If I combine 10.0 grams of aluminum and 25.0 grams of fluorine, which is the limiting reactant and which is present in excess? What mass of product will be formed? That is, what is the theoretical yield? And that is the definition of the term theoretical yield, the mass of product I expect to get based on my stoichiometric calculations. And then finally, how much of the excess reactant will be left? Well, before we begin, we know that because this is a mass-to-mass stoichiometry problem, I'm going to need molar masses. So let's just go ahead and write and/or calculate the molar masses we need. Aluminum, from the periodic table, has a molar mass of 26.98 grams per mole. Fluorine, a diatomic element, will have a molar mass twice of that given on the periodic table, which is 38.00 grams per mole. And for aluminum fluoride, I will calculate a value of 26.98 plus 3 times 19.00, or 83.98 grams per mole. So now, here's the problem. I start out with 10 grams of aluminum and 25 grams of fluorine, and I want to know how many grams of aluminum fluoride will be produced. So how do I figure out which of the 2 reactants gets used up first, and therefore controls the mass of product I expect, i.e. the theoretical yield? Well, there are a number of different ways of solving this problem. For simplicity, I'm going to teach you one method, which I think is the most straightforward, and that is calculate the theoretical yield twice, starting with the mass of each reactant. So I will calculate the mass of product I expect starting from 10 grams of aluminum, and then I will calculate the mass of product I expect starting with 25 grams of fluorine. I will get 2 results. Which one is the correct result? Well, if you think about it for a minute and consider the pancake analogy, you will realize that the smaller result must be correct, because that comes from the limiting reactant. So let's go ahead and do the problem. So I'll begin by calculating the mass of product I expect based on my 10.0 grams of aluminum. I'll begin by converting grams of aluminum to moles of aluminum. I will multiply that by my mole ratio, 2 moles of aluminum fluoride expected for every 2 moles of aluminum times 83.98 grams of aluminum fluoride per mole to convert from moles of product to grams, giving me an expected 31.2 grams of aluminum fluoride. But I'll repeat the calculation, now starting with the mass of the other reactant, 25.0 grams of fluorine. So So I'll convert from grams to moles by dividing by the molar mass, and I will multiply by the mole ratio. 2 moles of aluminum fluoride expected for every 3 moles of fluorine times the molar mass of aluminum fluoride, 83.99 grams per mole, to give me 36.8 grams of aluminum fluoride. They can't both be correct. Which is correct? The smaller one. The correct theoretical yield is 31.2 grams of aluminum fluoride, and that allows me to determine that the limiting reactant was my 10.0 grams of aluminum, because that is the reactant that led to the correct mass of product. Okay? Again, I cannot get 36.8 grams of aluminum fluoride from 25.0 grams of fluorine because there's not enough aluminum. Just like in the pancake analogy, I can't predict the amount of pancakes from 6 cups of mix because I only had 4 eggs. Exactly the same process. Now, the last part of the question is, how much of the fluorine will react? Well, we know fluorine is present in excess, so to calculate the amount of fluorine that's left over, well, just as the 10.0 grams of aluminum, the limiting reactant, controls how much product I'll get, that mass of aluminum also controls how much fluorine reacts. So again, starting with the grams of the limiting reactant, which everything starts with, converted to moles, I will multiply that by the mole ratio. 3 moles of fluorine used up for every 2 moles of aluminum I start with, times the molar mass of fluorine, tells me that 21.1 grams of fluorine actually reacted. Therefore, the mass of fluorine left over will simply be equal to the 25.0 grams of fluorine I started with minus the 21.1 grams of fluorine that reacted, or 3.9 grams of fluorine left over. So, on this page, I solved all the parts of limiting reactant stoichiometry problem. So to review, given the masses of each reactant, I determined the theoretical yield by calculating the theoretical yield twice and choosing the smaller result. The reactant that gave me that, in this case aluminum, is the limiting reactant. And then by using the limiting reactant, I calculated how many grams of the excess reactant reacted, and by subtracting that from the mass of the excess reactant I started with, figured out how much was left over. Now, one of the cool things is that you can actually check your work by using what's called conservation of mass. Okay? So I initially started out with 10.0 grams of aluminum and 25.0 grams of fluorine for a total mass of 35.0 grams of reactant. I ended up with 31.2 grams of aluminum fluoride plus 3.9 grams of fluorine in excess, which gives me 35.1 grams total, which within rounding is correct. So, suppose instead of isolating the 31.2 grams of aluminum fluoride I predicted, I only ended up in the laboratory with 28.3 grams of aluminum fluoride. This is called the actual yield. The actual yield is the mass of product that the chemist actually isolates in the laboratory. And very often, the actual yield is less than the theoretical yield. In true practice, you often end up with fewer grams than your stoichiometric calculations predicted. Why would that be? Well, there are a number of different reasons. Okay? It could be experimental error. Maybe you made a mistake in your calculation. It could be that the product decomposes or evaporates. Or it could be that there are side reactions. Some other reaction takes place that gives you something other than your expected product. Whatever the reason, the actual yield is usually less than the theoretical yield. So, to express how efficient our reaction is, we're going to calculate what's called the percent yield. Now, the percent yield is not the same as the percent error. You calculate the percent yield by taking the actual yield, which you measure in the laboratory, divided by the theoretical yield, which your stoichiometry calculations provide you, and multiply by 100. For example, suppose you're baking muffins, once again, food, and your recipe says you should get 10 muffins. What if you only get 9? What's your percent yield? 90%, because you only got 90% of the muffins you predicted. So, in our example, let's go ahead and calculate the percent yield. So, the actual yield was 28.3 grams. The theoretical yield was 31.2 grams. Divide, multiply by 100. That gives me a percent yield of 90.7%. And because that's based on based on measurements that have sig figs, we round the correct number sig figs. So, to summarize, here's what you should be able to do. Given a balanced chemical equation and initial masses of both reactants, and there will only ever be two, you should be able to identify the limiting and excess reactants by calculating the theoretical yield and seeing which reactant gives you the smaller and therefore correct theoretical yield, calculate the mass of excess reactant left over, and then finally calculate the percent yield given the actual yield. That's pretty much it for our unit on stoichiometry.